Hello and welcome to this demonstration as part of the course for the Secure Systems Engineering. So in the previous demonstration, we had taken a particular code, a program in C, and we had actually looked at a vulnerability that was occurring due to string copy. And we seen how overflowing a particular local buffer more than 100 bytes could actually create a segmentation fault. And we'll use GDB during that demonstration to actually see that the return address was overwritten due to the buffer overflow. In this particular demonstration, we will work from there and we will see how we can enhance that attack and inject a particular payload into that program and force that payload to execute. So the payload that we will actually consider is to create a shell. Now, such payloads where a shell is created is very popular in this kind of examples, because once an attacker has a shell, he has quite a bit of control on the system. Suppose an attacker actually is able to obtain a shell in a system, and if you assume that the shell has super user privileges, then the attacker has super user privileges in that system and can do anything that a root user can do. So, as before, we will be using the codes that is available with the Bitbucket repository. So, these codes are present in NPTEL codes module 2. Look at this, and the code that we will be looking at is the test code. So, recollect that the test code had two functions, a copier function and a main function. The main function took the argv as command line arguments, and it passed argv1 to the copier function. The copier function had a character pointer str which had this pointer to this particular string, and then invoked string copy, taking character by character from str into this buffer. Now note that the vulnerability occurs over here because buffer is just of 100 bytes, while string copy would continue to copy into buffer until /0 or a null character is obtained in str. So, as long as there is no null termination character, str copy will continue to execute, copying byte by byte into buffer and resulting in a buffer overflow. The first thing to actually do when creating this exploit is to identify at what point during the execution or what payload would actually cause this test code to stop executing. So, in order to do that, we use a small script called find payload. So, find payload looks like this. It is a small Python script, and it essentially creates a string A's, in this particular case 108 times. So for example, if I add say 8 over here, then a print padding would actually print A 8 times as follows. So, find payload would print A 8 times. Similarly, by changing this over here to say 64, I would get a string of length 64. Now, in order to pass this as the command line argument to test code, we do the following. We run test code as follows. The first thing we do is to put the output from find payload into E1, into some file E1. So, cat E1 comprises of 64 A's. And the second thing is to send E1 as an input to test code. This is done as follows. Cat E1, and we see what happens here is that test code takes the input from E1, which is 64 A's, and executes. Since 64 is less than the size of the buffer defined in test code, so there is no problem, and there is no overflow that occurs, and test code completes successfully. On the other hand, if we increase the size of A, from say 64 to 128, let us see what would happen. So, we do this as follows. 128, run this and store the output in this file E2. So, /find payload and store the output in E2. Therefore, E2 now contains 128 A's as follows. Now, if we run test code and we would have this buffer overflow as we have seen in the previous video, and test code would segmentation fault and would have a fault. Now, by changing the length of this particular string, we would be able to identify the exact length of the input which causes this problem. If I change this to say 104, run the find payload, store the length of E2 of 104 byte A's in E2 and run it, we see that it works. So, 104 is not going to solve our problem. On the other hand, if I make it 108 and do exactly the same thing, we see that the done gets printed, as well as after done there is a segmentation fault. This occurs precisely because with a length of exactly 108, the frame pointer which is stored on the stack is overwritten, but not the return address. Therefore, after the function completes its execution, which we will see as in the code, therefore, after the copier completes its execution, we note that the frame pointer present in the stack has been overwritten, but not the return address. Therefore, the return can come back to the main and printf done would get executed. However, since the frame pointer has been modified, the main will not be able to exit cleanly, and that is why you obtain a segmentation fault after the printf completes execution. Now, if on the other hand we change padding from 108 to 112, which means that we have 4 extra bytes of padding, what we can expect is that it's not just the frame pointer that gets manipulated, but also the adjacent memory, which essentially is the return address, would also get modified. So, in such a case, what we can expect is that the copier function will not be able to return back to main. So, when we run this program again with a payload of 112 instead of 108, we would see that the done statement is not executed. This is because the return to main has been modified, and the copier is trying to return to some invalid argument at a location 0x41414141, which is essentially the A's that you are inserted in the return address location, and which has illegal instructions. So, the next thing we will actually look at is to force a specific payload to execute. So, we would look at this particular file called next_payload, which looks something like this. So, it comprises of 4 parts. One is no ops, then you have the shell code, then you have some padding, and finally you have an EIP. So, what we do want to do with the shell code is to fill the buffer with all of this. There should be 64 no ops, then a shell code present over here, which is of 32 bytes, and then we have some padding which is of size 112 minus 64 minus 32 bytes, and finally a value of FFFFCF70. So, what exactly is this value is what we will actually identify. What we expect should happen during the buffer overflow is that after this 100 bytes is filled, the frame pointer which is stored in the stack will get overwritten. Next, the return address to main would also get overwritten. So, what we want is that this return address should now point to this shell code. So, we would require to know where exactly in memory this shell code is present, and in order to know this, we would need to use GDB. So, we will open another terminal and run GDB as follows: test code. We list and we put a breakpoint in line number 5. Okay, and run with some input, say A's. Okay, and at this particular point, we look at the contents of the stack. So, that, as we have seen before, would contain x32x $ESP, which is as follows. Now, if I disassemble main, the return address after copier is 0804847A, and we want to know where this return address is present on the stack, and we see that this return address is present over here. This is at the location FFFFCFEC, and furthermore, we want the address of buffer. So, that is obtained from the location info locals and p/x ampersand buffer, and we note that FFFFCF7C is where buffer is present. So, that means the buffer is actually present somewhere here. So, what we do is ideally we would like to fill our payload starting from this location. So, starting from this location, we would want our payload, that is the shell code defined over here, to be present. However, to get a better alignment, what we do is we add some no ops initially. So, the no ops is present by this opcode, is given by this opcode 90, and whenever the processor sees this opcode of 90, it is just going to skip the instruction or do nothing in that instruction. We fill in no ops starting in the beginning of the buffer, and then at some offset, in this case 64 bytes, we fill in the shell code. Now, we need to jump back somewhere in the no ops at a reasonable alignment, so that the shell code executes. So, a lot of this is obtained by trial and error, and what we found that if we specify the location FFFFCF70, it would indicate it would actually work. So, we will see what happens when we give such an input. So, first of all, we create the shell code that we want to execute as follows. So, we say next payload and store it in this file called E3, and then we run GDB with test code, break at line number 7, which is at the end of string copy, and then run, giving the newly formed payload as the input. So, this is done by cat and E3. So, which would take the input from the file E3 and run with that particular input. So, given this, let us see what has happened is that the copier has executed, further string copy has executed, and since the string which we have given is much larger than 100 bytes, therefore, buffer has overwritten, and the string has been strategically created in such a way that the return address present on the stack has been replaced with a specific return address, which forces the payload present in the buffer to execute. So, let us see this more in detail. So, we will print out the stack as before, x32x ESP $ESP. We would look at the payload that we have created, and we see at this particular point where buffer actually starts is supposed to be present, we see that there are 64 no-ops comprising of the byte 90. So, if you actually count, it would be like starting from 90 over here to this particular thing, there would be 64 bytes of no-ops. Then we would see that the payload is actually present starting from this location. Note that the alignment is based on Little Indian. So, therefore, when we specify C3, C089 C3, what you actually see here is the Little Indian notation for the same. So, the next 32 bytes which will comprise of the shellcode. So, what the shellcode actually does is that it encodes the machine operations, which actually creates a shell. We will not go into details about how the shellcode is created right now. So, you could look at the previous video, or there are various tools online which would create these shellcodes for you. So, if you actually look at this, we see that these are the first 4 bytes of the shellcode in the Little Indian notation, next 4 bytes and so on. Now, the shellcode ends over here with 420B CD80, which is here 420B CD80, and then we have a lot of padding which is present. In fact, we have 112 minus 64 minus 32 bytes of padding. That we see is the padding with A's, which is actually present from here to here. So, there are 1, 2, 3 and 4. So, that ends up being 64 bytes of padding, which is 112 minus 64 minus 32. And finally, we see that this location, which was supposed to have the return address, so this location is overwritten with the value FFFFCF70. So, what this means is that when this copier function completes its execution, it's going to pick the memory contents from this location and put this into the EIP register. So, corresponding to FFFFCF70 is this memory over here. So, what is going to happen is that the instruction pointer would point to this location and it would pick up each byte from here. This is 90, 90, 90, 90 and start executing these no-ops. So, all of these no-ops get executed, and then your actual shell code, which is starting at this location, would then get executed. Eventually, by the end of these 32 bytes of operations that get executed, your shell would have been created. The shell gets created ideally by a system call to the operating system using an interrupt ATH, which tells the OS that a new process has to be created. So, this is what is actually happening over here. So, let us actually run this code and see that a shell is executed. So, when we run it, so we can run it outside the GDB, and we can run it as follows. So, we can say / test code cat E3. / test code $cat E3, and what we see is that a shell gets created. So, this shell is the sh shell. So, we can do all the shell commands. We can also look at ps. that is the processes that are executing in the shell, and we see that in fact there are 3 processes. PS is the process that is the command that we have given, and the parent for this process is the SH process, and the original bash shell which was created with this terminal is present here. So, in this way we have seen that we have injected this particular code called test code.c with a payload. We force the buffer to overflow, and the payload which was present in the buffer to execute. So, many of the malware actually use this particular technique. They obtain a payload, and once an attacker is able to obtain such a payload, he can do anything in the system, like for example delete all the object files like this and so on. Thank you.